It's already how many days? The 5th day of March. Okay. If you can recall, the midterm exam is in April the 9th. So, in order to prepare for this big event, I look for bigger classroom because we have a class of 90-something students. I cannot recall exactly, but this room can only accommodate a little bit more than 100. But I failed to get a bigger classroom, like lecture theatre. So you may have to just sit like this, even though a lot of students skip class, but I think during the exam should be full house. I expect. Otherwise, they should never attend again because they will fail. And so, yeah, it's very frustrating because it's not because I don't trust on you, and sometimes accident always happens. Okay, and I will maybe put in more TA in order, but you may not have time to look around because it should be quite easy looking on the question because I set the questions already. And later, maybe 1 or 2 weeks later, I will post the sample questions and also some more difficult multiple choice on the LMES for you to review. I hope there will be no overlap between those questions and the exam question. And because we are from different sources, and but I think it will be very useful for you to test yourself whether you really understand what I'm talking about. Because according to some informal information, almost 50% of the class did not understand the lecture for the lab. I don't know why. Okay? And some students request video recording. I think this is a good idea. You can review it 10 times, right? If you don't understand the lecture. This classroom, we can do video recording. But I understand, I think they can move, but maybe do some makeups, okay? During the lecture, I mean for the female instructor. Okay, otherwise look bad. Okay. But none of you complain about the language in this class. I don't know why 50%. So, okay, let's get the live going. So, in this week, we will wrap up the central pathway for energy metabolism. Because we're going to use 2 lectures or 2 sections to cover this electron transport, oxidative phosphorylation, and its relation to oxygen. Because everybody should understand when we talk about oxidative phosphorylation, there must involve the giving out of electron. Eventually, we have defined an ultimate electron acceptor. Otherwise, you cannot get things done properly. So oxygen, in this case, or in our energy metabolism, plays a role as the electron or terminal electron acceptor, generate water by accepting 4 electrons That's what we call tetravalent reduction. Tetra means 4. Okay? And hope this work? Yes. So this is the mitochondria again. This is my pet. Okay? Because I research on mitochondria. In order to understand how mitochondrial functioning affect aging, age-related diseases. How mitochondria can be made use of to control your body weight. All this can generate wealth, okay, by inventing new agent, working on that. Of course, if you end up to be a professor, forget about money, okay, because you don't have any time to think about how to earn more money. Just look at the mitochondria. So it's a double membrane organelles and supposed to be a symbiotic microorganism get into a mammalian cell and tested and responsible for generating energy. So that's why its membrane structure organelles is different from other eukaryotic organelles. So the inner membrane is the site of interest in terms of oxidative phosphorylation, where the enzymes or the protein arrange in such an order that electron transport should be conducted in an orderly manner. Okay. From this on, we will get some foundation knowledge about oxidation reduction, then you understand why electron could be transported from one protein to another and eventually to the oxygen molecule. Of course, all this process involve enzymes. Okay? And those electron transporter, majority of them are proteins. Of course, protein contains what? Sometimes coenzyme in order to carry out the job of electron transport or metal cofactor. Usually iron and also copper use as the metal cofactor for the enzyme. Simply because, anyone understand why copper and iron? When we talk about reduction and oxidation, why always these two metal ions? What is their name? Give me the name. They call, yes, there's a name called transition. They're transition metal. That means they can switch from one oxidation state to another oxidation state. For example, if they switch from, the ion switch from 2 positive to 3 positive oxidation state, how many electrons putting out? 1. Okay, and this is very characteristic of this transition metal ion, and enable them to be a pair in this electron transport. This is the schematic representation of an electron transport train. So complex 1, a group of components. Okay. I think a protein, there is some not well defined, what we call is the iron sulfur cluster, and we call complex 1. And NADH will donate electron to complex 1 to initiate what we call an electron transport process. And there's a Q here. What's this Q? Coenzyme Q. This is a very important pair. We will explain later. Okay? And there's a complex 3, complex 4, and complex 1. So you are observant enough, then you may ask, where's complex 2? Let's complex 2. Anyone can tell me? Complex 2 share with citric acid site. Remember the succinate, the hydrogen. Okay, actually the enzyme, when we talk about TC cycle, the enzyme is actually in close association with the inner membrane. Okay, and that's the complex 2. So during electron transport, complex 1 give electron to coenzyme Q. Complex 2 also give to coenzyme Q. In other words, if the electron carrier enter the electron transport through complex 2, it will skip complex 1. And it is FADH2, if you can recall, right? Generated by the succinate dehydrogenase. Okay? Some of you ask me, why FAD, not NAD? Because when you talk about oxidation and reduction, you have to pick an appropriate electron acceptor. Okay? Just happen FADA is okay for that reaction. Okay? In terms of energy difference between the electron donor and electron acceptor. And complex 4 is where oxygen being reduced. I already mentioned to you tetravalent reduction. And in fact, in this complex 4, the enzyme oxygenase, okay, cytochrome oxygenase is a big enzyme. It contains different active sites. And during the process, later will explain you why oxygen has to be reduced by 1 electron at a time. That means when you want to reduce the oxygen molecule, you can't just add 2 electrons at the same time. You have to add 1 at a time by 4 times. Then think about what will happen. How many intermediates will be generated in this process? You add 1 electron of oxygen, you generate 1 intermediate. 2 electrons, second intermediate. The third electron, 3 intermediate. Right? That means in this process, you will generate something I call reactive intermediates. Because you add 1 electron to the oxygen, it will create an enormous demand for more electrons in order to fulfill the electron first. So, but these reactive intermediates are tightly bound to the enzyme without releasing out to the mitochondria to a large extent. Okay? Imagine if this intermediate getting kicked out from the enzyme, what will happen? Those intermediate is in a state of electron thirsty. What will they do? They will oxidize the mitochondria, proteins, mitochondrial membrane, and you will become rusty inside your cells. So later, in the later section of this topic, we'll talk about what will be the consequence. How are we going to deal with it? Okay. So this is just some preliminary background for you to bear in mind. So if you don't understand, don't be panicked. We will talk about it later. And besides the reduction of oxygen, serving as an electron acceptor, one important aspect of electron transport in the mitochondrial membrane is for generating ATP. Okay, through this complex bond, also called ATP synthase. This is a macromolecular protein, and regarded by scientists as a miniature of a motor, rotor in the cell. When it turns, ATP will be generated. It just turns, ATP will spin out. But what makes the rotor turn? That's the point. Anybody can suggest any information from this diagram, okay? All the answers in this diagram.
The part 2 of the hydrogen.
What is this? This is proton. So this is inner membrane. This ATP synthase is a transmembrane protein. As a channel, allow the proton to go through. If I write this is positive, this is negative. That means the concentration of proton at the outer side of the inner membrane is higher than the inner side due to one reason. When electron transport goes to complex 1, complex 3, and complex 4, it will just pump one proton outside. Okay? And eventually create a proton gradient which can drive the synthesis of ATP by this ATP synthase through the intermediates of this channel. When proton go through, somehow it will trigger the conformational change of protein component and will turn this protein by 180 degrees. So of course, don't be panicked. Now, we will go over this again. This is just an overview diagram. So, to conclude, electron transport will generate a proton gradient. This proton gradient would be used to drive the synthesis of ATP. So, do you figure out how energy being transformed in this process in terms of the nature of the energy? First of all, is what kind of energy? NADH. Is electrical potential, right? For the electron. When it transfers, and then you pump the proton, the gradient is a chemical gradient. And this transformation from electrical potential energy to chemical potential energy, and eventually this chemical potential energy will be used to drive the ATP synthesis, and the energy being harnessed in form of chemical potential energy in the phosphor and hydride bond. Then you understand how energy being transformed in this process. So how energy being transformed in this process? Waterfall, you fill a dam, trap the water. Okay, this water reservoir store a lot of potential energy, and then when water go through the dam, falling down, go through the tubes, and then turn the mobile. And the mobile is located inside a big magnet. Okay, when the magnetic field is being cut by turning of the mobile, what will generate? Oh, you have studied physics. Faraday law. Okay? Then how you generate electrical energy? You change the potential energy, geographic potential energy, physical potential energy into electrical energy. So by similar process, okay, of different form, cell can generate ATP. And somebody told me, if you want students to understand or only understand or learn the topic better, you better scare them with some disease, okay? Or highlight the topic with some disease and indicate the significance of studying mitochondria. But actually, mitochondria, due to the important role in energy production, anything wrong with the mitochondria can cause a lot of trouble. Like the most obvious one is mitochondrial myopathy. What's myopathy? Something wrong with the muscles. Muscle need energy, particularly your muscle, the muscle in your heart. Okay? If you want to find the cell with the highest density of mitochondria, go for the heart cell. Because the heart needs a lot of energy by oxidative phosphorylation. So, if something wrong with mitochondria functioning, cause symptoms like weakness, cramping of muscle, severe fatigue. I'm working on fatigue. How to counteract fatigue? Do you know why you feel fatigue? Yeah, you must say, okay, yeah, go to play soccer. I'm very tired. Fatigue, okay, fatigue is an extreme form of tiredness, okay? Do you review or watch a TV advertisement? There's a man with a mustache. Somebody call him for soccer. So he has different kind of excuse not going because he felt tired. That means you watch TV. Okay, tired is a matter if you boil down to biochemical mechanism. Why tired? Because, for example, you want to grab your watch. I want to move my arm, but the energy production in my muscle cell cannot meet this demand. Then I feel tired. I don't want to move. Even though your watch is very fancy, I don't want to grab it. Okay? So that's why it's very weak and severe fatigue. It's a severe form of tiredness. Alzheimer's disease also related to mitochondrial dysfunction in the neuronal cells, cause loss of cognitive function and memory. Do you know what's cognitive function?
Something related to
learning, right? Just cannot memorize anything and cannot recognize things. So this is very severe disease, one of the severe debilitation because Alzheimer's cannot kill immediately. Okay, an Alzheimer's patient will suffer for maybe 10 or more years. And the kind of care demand could produce a lot of problems. Okay, so now scientists working on preventive approach because there's no cure for Alzheimer's. What can you do is try to prevent the occurrence of Alzheimer's disease and do something new with the mitochondria. So if you can prevent the mitochondrial function being lost, then you may find a method to prevent the Alzheimer's disease. Another neurodegenerative disease also related to the mitochondrial dysfunction, and I don't want to go into detail, don't want to scare you too much. But one thing that mitochondrial decay is a leading hypothesis for aging. Okay, why we age? Because our mitochondria function decline with age and produce a lot of age-related diseases. That's why I'm interested in this area. It will generate a lot of interest. Okay. not the interest in your bank account, it's interest for the public. Okay, in this section, so we have some key questions to address in my lectures. Where in the cell are electron transfer and oxidative operation carried out? Okay, so we're going to learn this. What are the reduction potential? We're talking about different kind of potential. What is your potential? Definitely not reduction potential. Okay? But when we talk about electron transfer, we have to learn the concept of reduction potential. That's the background knowledge. How are they account for the free energy changes in redox reaction? After all, this electron transfer is a reaction, right? It's a redox reaction. How would we transform this redox potential into a term that we always want to know regarding a reaction, which is free energy, right? So there's an equation, don't worry, very simple. And how's the electron transport chain organized? Okay, actually I showed you already. How does a proton gradient drive the synthesis of ATP? Of course, this is very important, and the scientists investigate this or elucidate this mechanism, earn another Nobel Prize. And what is the PO ratio? Force flow to oxygen ratio, the mitochondrial electron transport, and oxidative phosphorylation. You're going to learn this. How are the electrons cytosolic NADH fed in the electron transport? Okay. Actually, this highlights the main point concerning about electron transport. As I promised, I won't go into very detail because it won't work. Okay? You just understand the basic principle. Just like this. Okay? Very simple. Central metabolic pathway. From glucose, glycolysis become pyruvate, and then acetyl-CoA enter the TCA cycle, produce a lot of NADH. So now today, we start from NADH or FADH2. Why you talk about FADH2 too? Which one is the major player, FADH2 or NADH? Because
more is generated.
Oh, 3 to 1, right? And also 2 from the glycolysis. So that's the major player. So FADH of course important in the sense that complex 2. Okay, is for the FADH2 to start the electron transport process. The way that I deliver this information to you is actually tell you how to organize your information. Okay, in order to consolidate your memory right after the lecture. Even though you just have the lecture, you get all I deliver in the lecture, you can pass the exam. That's the point. Electron transport go through different carriers, eventually generate ATP with the regeneration of those electron carrier, which is very important. Otherwise, there's no substrate for TCA cycle, no substrate for glycolysis, right? So this regeneration is very important on this electron transport. How about if there's no oxygen? What will happen? Or not enough oxygen, then something happen here. Okay. Pyruvate will convert it to lactate and then generate the oxidized NAD. It's better than nothing. Okay? Even though you generate 2 ATP, that could be life-saving. Okay? During emergency situation. To energize your muscle, to get away from dangerous situation. Okay. if you look at the anatomy of mitochondrion, there's outer membrane, intermembrane space, inner membrane, and matrix. Outer membrane is basically permeable to most of the molecule because it contains protein called taurine. They form pore outside or on the outer membrane. So how mitochondria control the import and export of molecule is through the inner membrane. And the inner membrane contains transport. Okay, protein molecule that can carry molecule from the matrix to the cytoplasm, or from the cytoplasm to the matrix. And this process, the shuttling process, is very important. You will learn it later. Okay. How about the organization of the inner membrane? The inner membrane is flow into different structure called invagination. They form cristae. Cristae is a plural. Crystal is singular. So many they flow inside, okay, into different cristae. What's the point? Why? Yes. Just like in the small intestine, there are a lot of villi, right? They also flow into different cristae-like structure. We increase the surface area for absorption of the digested food material. Okay? We flow, increase surface area, that means more electron transport protein to accommodate the process, and then the capacity of generate ATP in the mitochondria increase. Okay, there are 4 protein complex, as I already mentioned to you. Okay, this is a more illustrative diagram. Of course, it shows you complex 2. Okay, complex 1, NADH, donating electron, 2 electron complex 1. And then transfer it to coenzyme Q, of course, through a series of processes. And the FADH2 through the complex 2 also donate the electrons or pass the electron to coenzyme Q. And then coenzyme Q here will then pass the electron to complex 3. One crucial point I have to mention to you. That is complex 2, both complex 2 and complex 1 and complex 2. There are 2 electron transporters, or the electron carrier inside them can carry 2 electrons. Just like when I asked you, how many electrons NADH carry? 2. How many electrons FADH2 carry? 2. So, however, when you look up in the text, the electron carrier in complex 3, most of them called cytochrome. Cytochrome, different kind of cytochrome. Cytochrome contains a metal cofactor called ion. How many electrons can ion carry? 1. Now immediately you know the electron transport process has to switch from 2 electron transport to 1 electron transport here, from 1 and 2 to 3. How this could happen? Coenzyme Q is what we call a shuttle. Because coenzyme Q can carry 1 electron. Okay? Can serve as a shuttle. Actually, go through a very complicated cycle called Q cycle. You spin one electron. So effectively, because I skipped this part, in order not to scare you again, okay? This is a Q cycle, but this process, though very complicated or very difficult to understand, but if you spend some time, you will understand how this Q cycle operates. But outcome is, okay, to sample electron from electron carrier to one electron carrier. So this plays a very important role. And also, during this Q cycle, accidentally, due to this 2 to 1 transition, there's a chance that one electron may spin out, or you may say leak out from the electron transport chain. What will happen? This electron will combine with any oxygen in the matrix and form reactive free radical. Okay? So bear this in mind first, okay? Don't worry. But now we are in complex 3, one electron transport, and then to a mobile electron carrier again called cytochrome C. Cytochrome C is kind of loosely associated in the membrane, and we transport the electron from 3 to 4, complex 3 to complex 4. And complex 4 is where contain the enzyme called cytochrome oxidase. Cytochrome C oxidase to reduce oxygen molecules to water. As I already told you, this process is very important in the sense that this cytochrome C oxidase will tightly bound all the reactive intermediates until it is safe to release a water transport. Okay? Okay, this is what we call electron transport. Okay, before we go further, a little bit of high school chemistry in order to recall your memory or recollect your memory. So in acid and phase reaction, just use the same concept. Acid is a proton donor, and a conjugate phase, and then with a proton. Okay? So how to define a strong acid? What should a strong acid behave? So in terms of the proton projection, if I'm a strong acid, I will very much happy like to protonate you. Okay, this is a strong acid. Okay, using the same concept to reduction and oxidation. So look at this half redox reaction. Any reduced compound, okay, we will change to oxidized compound. So reduce and oxidize is just a matter of relativity. Okay? So reduce become oxidized, you give out an electron. Okay? That means any reduced agent, they will have a tendency to give out a domain electron. Just like for an acid, we have a tendency to donate proton. Same principle. So for complete redox reaction, there must be oxidation and reduction reaction. For reduction, it becomes oxidized or oxygen being reduced. Okay, this is a complete reaction. Look at this example. Q plus ion, couple 1, with ferric. And in this case, cubic will serve as a reductant. The ferrous ion will serve as an oxidant. Because this reaction will tend to go in this direction, that the Q plus ion will become cupric ion. Cupric, okay? 2 positive. And at the same time, the ferric will become ferrous. This is what we call redox reaction. Okay? So for reductant, the donating electron, of course, is cell being oxidized. For oxidant, accept electron, which is cell being reduced. Right? You accept the electron, your cell becomes reduced. So now you understand this relationship. And actually, look at this electron, the electron transporter in different compounds. They are arranged in such an order that they have this intimate electron donor and receptor relationship. Of course, if you look at those at the top, they will have a higher tendency to donate electron to those just right below. Right? Then you can form the electron transport train. Just like you stop the water filling the dam. Okay? The water will be filled. And then the water will tend to flow from the top to the bottom according to gravity. So this difference in reduction potential would be the same as the gravitational force of the electron. Just use the same concept. You have this table, okay? To miss out all the oxidant and reductant pair. You want to work out the reduction potential or the free energy from the reduction potential for certain reactions. You just use this table. Okay, just a simple interpretation of this table. Of course, I won't require you to memorize it. This is not biochemistry 20 years ago. Okay? The couple, the higher the redox couple on the list, the stronger will be the reducing agent. That means those relatively on the top, okay, higher than the other couple, they will tend to be a reducing agent. That means they will tend to donate the electron, give out the electron. They have a higher tendency of giving out the electron. The lower redox couple, say you compare acetate and succinate, these two couples, then the acetate would be a stronger, this couple would be a stronger oxidizing agent. Okay? That means electron will tend to go from this couple to the couple at the lower. So it's a matter of relativity. As I already mentioned to you, the arrangement of different electron transporter, loyalty to the electron transport train is arranged in such an order under this principle. Okay, look at one example. How you convert the electrical reduction potential of certain reaction into free energy. Okay, this is the equation. Okay, worked out by I don't know who. Okay, a scientist. So the relationship between delta G and reduction potential, the delta D of certain in a reaction, in a redox reaction is like negative n Faraday constant times the delta E of the two half reaction. Okay. So okay, look at this real example. You have ethanol, you see what is the delta G of this possible reaction. Ethanol with NAD oxidized being oxidized to acetaldehyde to generate NADH. That means the electron being donated by ethanol, okay, resulting in the formation of acetaldehyde. Okay, we do some analysis. Okay, if this NAD oxide become NADH, the standard reduction potential or biological reduction potential is negative 0.30 volt. Okay, for acetaldehyde to here, this is just from the table, right? It's negative 0.197. However, in the reaction, it works the other way around, right? It's the any aldehyde become ethanol. So you have to, the ethanol become aldehyde. Okay, you have to change this sign. Instead of negative, become positive, right? Because this is in this direction, ethanol to acetaldehyde. So for this reaction to happen, you add up, and the net delta E would be negative 0.123. Well, so the value, the important thing is that you have a negative delta E value for this transformation. Okay, after looking the two half reaction. And from this equation, you substitute the delta E, and you have a positive delta G. Then you have to determine whether this reaction is thermodynamically favorable under biological standard condition. Is it but no? That means you have learned something about free energy. Okay? Now you understand that for negative delta E, you have positive delta G. Okay? That means not favorable. In contrast, if you have positive delta E, then you have negative delta G for certain reaction, then it's favorable. And that's the whole message, or the only message I want to convey to you. Okay? It's just opposite relationship due to this equation. Okay, interesting question. How many ATP will be generated by oxidizing one NADH, 1 mole, example? Okay, one easy way is to look at the free energy change. Okay, what is the free energy change of oxidizing 1 mole NADH? Okay, of course, by reducing oxygen to water. Okay, 2 electrons, you can only generate 1 mole of water. Okay, and the delta G is negative 220. Favorable. Now we know the standard biological delta G for ATP synthesis or hydrolysis the same, right? Negative 31. Okay? It's quantum amount. And before you calculate or estimate how many ATP will be generated from oxidizing 1 mole of ATP, you have to take into consideration about the efficiency of energy transfer. Okay? In the mitochondria, it's about 40%. Okay? Some energy will be lost as heat. That's why when you exercise, you're getting very warm. Okay? So then after this, how many discount? 40%, no, 60% discount. Okay, because you get only 40% from this energy, from this reaction. And then times 40% and over 31, or approximately 3 ATP. Okay, just a rough estimate. Don't remember this. This is wrong. This is theoretical value. Okay? Later I will tell you why this is wrong. According to the most recent finding, it's less than this. Okay? Overall, if you base on this free ATP and you calculate the total amount of ATP generated by oxidizing 1 glucose, it's a lot. 30 something, 36 or 38. But actually, the actual number is less than that. I will tell you later why. But as long as you can move, it's okay, right? You can eat, you can external supply of glucose. Why bother about the efficiency? Doesn't matter. Okay, this again, we advance the diagram to look at this. just tell you a trick how to memorize this electron transfer. Okay, you have complex 1, complex 2, never mind about the detail. I've told you there's some what we call iron sulfur cluster. Okay, some protein, enzyme, and cluster, and then eventually electron go to the coenzyme Q. This is the 1 electron subgroup, and then go to complex 3. Okay, look at complex 3. What is CYP? Cytochrome comes into play, which is a very important protein molecule responsible for this oxidation reduction reaction because it contains iron as a metal phosphatic group, okay, which can undergo the switching between oxidation number. That's why it can participate in oxidation and reduction reaction. Even cytochrome isomer. Start from cytochrome B with this iron sulfur centers, C, cytochrome A and A3, spanning different cytochrome between complex 3 and complex 4. Okay, in complex 3 you have B and C1. In complex 4 you have A and A3. When I was little, as you, I memorized this BCAA. But now you are lucky. You don't have to memorize. But if you really want to memorize, okay, BCAP, okay, BCAP, and that's how the sequence goes. Because in our time we have to memorize this. Not you. You are lucky. When I was little, okay, I have to memorize this. And then eventually the electron goes to oxygen. 1, coenzyme Q, complex 3, and then cytochrome C. This is very important molecule. You will find it out later. Besides as an electron substance, okay, 1 electron carrier. It is a very important player to confirm a role of mitochondria being a coordinator of life and death. Okay, cytochrome C. Okay, look at this diagram, indicate to you the electric reduction potential with different pairs in the electron transport train. Oh, just going down slope, downhill, right? And they are arranged in such an order. That means, okay, they have to arrange in this order. Otherwise, with the electron carrier at the top has a higher tendency of donate electron when compared with the later. Otherwise, how could you enable the flow of the electron? Okay? This is a very simple logic. And when you compare NADH and oxygen, so it's a lot of free energy being released, okay, when compared with reduction potential. So, how this could be worked out? Now, the scientists work for different decades, right? They work out this sequence. Now we understand, okay, they are arranged in such a order. But the construction of this graph necessitates a lot of experimental investigation. Okay, and finally, eventually, this becomes what we call textbook knowledge. We can use different approach. The one that you use in your lab, spectrophotometric techniques. Have you gone through the spectrum measurement already? Hemoglobin? Was it interesting?
No, he won't go with this Friday.
With the spectrum? Oh, this Friday? Okay. So you measure the spectrum. Okay, this is one kind of technique we used many years ago. to investigate. I already told you in your lab it's a basic biochemical technique, right? You want to advance biochemical technique, do the research project in the research lab. Use specific inhibitor and artificial electron, etc. That's why we can pinpoint different electron transfer. How? We'll go into that later. The ultimate approach, isolate the mitochondria, okay? And if you suspect, okay, these two are in a close association responsible transfer, reassemble, reconstruct, like the crime scene, right? You want to obtain evidence of certain crime committed by certain person. If you pick, you caught that, if you caught that individual, the criminal, you go back to the crime scene to reconstruct what happened. And that would be the evidence submitted to the court. Biochemistry is the same. You say, okay, this assembly should be what happened in the cell. Please do some what we call reassembly. Okay? Do some sub-assembly to demonstrate it really works like this. Before you're getting too fatigued, 5 minutes break. Mentally fatigued. Oh, I forgot my water. 5 minutes up and down.